All right, let's take a look at 4.6. This is the last section here. Or no, this is 3.6. I don't know why it says 4.6. That's just a typo. All right, counting rule, factorials, combination, and permutation. So you have the counting rule is if an experiment consists of 3 steps with m, n, and k outcomes, then the total number of outcomes, you're just going to multiply. So it's m times n times k. For example, at a fancy restaurant, you have a choice of 4 appetizers, 6 entrees, 3 desserts, and 2 choices of beverage. How many different possible combinations of a meal do you have? You would multiply all of those. You would go 4 times 6 times 3 times 2. So 4 times 6 times 3 times 2. 144 different ways that I could come up with that. So you don't have to actually write them all out. You just multiply. Okay, so for example, consider 3 tosses of I think I meant to put dice there, so make that dice. So consider 3 tosses of a die. How many final outcomes does this experiment have? How many final outcomes exist for an experiment consisting of 4 tosses of a dice? Okay, so you have 6 possible outcomes in a dice. So 6 times 6 times 6. 3 different times would be just 6 to the 3rd. So 216. If I did that 4 times, it's 6 to the 4th. Okay, so the total number of outcomes raised to the total number of experiments. So that's going to give us 1,296. Okay, factorial. Factorial is a mathematical computation, is a total number of ways that you can arrange items. It is the product of integers n to 1. So the symbol for factorial is an exclamation point. So if you see n exclamation point, that means n factorial. So for example, let's say I want to do 5 factorial. That is the product of the integers 5 to 1. So it's 5 times 4 times 3 times 2 times 1. Which is 120. Now, let's look at example 6.2. Consider a group of 10 marathon runners. How many different orderings exist for 1st through 10th place? So that is 10 factorials. Now you don't have to actually do that in your calculator because as you can imagine, as you get to higher numbers, it's kind of a pain. There is a command in your calculator for this. Okay, so if I go 10 math over to PRB, it's going to be number 4 there with that exclamation point. Okay, so it's math over to probability, then that exclamation point, it does the factorial for you. So it's 3,628,800. Okay, so you would go 10 math over to PRB, and then your exclamation point, and then enter. All right, and then we're going to use these in some formulas for combinations and permutations. So in combination is going to be the number of ways a certain number of elements can be selected from a larger group of elements. In combinations, order does not matter. Here is the formula for it. So you have n, c, x, or r. What does it have on our formula sheet? It has x on our formula sheet, so I'm going to use x. So n, c, x, where the c is normal, these are subset down a little bit. It's going to be n factorial over n minus x factorial, and then x factorial. Okay, so a teacher wants to divide a class of 15 students into groups of 5 for a class project. How many possible groups of 5 students exist? Okay, so the order is not going to matter. I'm just putting students into groups of 5. So it's 5, choose 15 when I'm looking at this. So the larger number is the x. Okay, the smaller number, like I'm putting into groups of 5. So it's 5, choose 15. So, no, it's not. It's 15, choose 5. I'm saying that backwards. Choose 5, because I'm only picking 5 out of the group of 15. So I have 15, I'm choosing 5. So the n is going to be 15. The x is going to be 5. So 15c5. Okay, now there's a couple ways of doing this. You can do this algebraically. You would have 15 factorial over 15 minus 5 factorial, and then 5 factorial. 15 minus 5 is 10 factorial, so I would go 15 factorial, 10 factorial, 5 factorial. And then that would give me, let's see, if I go 15, 14, 13, 12, 11, 10, I can stop there at the 10, because I'm going to keep going 10, 9, 8, right? But I have this 10 factorial here that I can cancel with that. And then I have this 5 factorial in the bottom. 4, 3, 2, 1. So I can cancel these 10 factorials out. Okay, I can also do some reducing if I really want. I could do 15 over 5 would give me 3 over 1. 12 over 4 would give me 3 over 1. 2 into 14 would give me 7 over 1. So I really could do 3 times 7 times 13 times 3 times 11 over 3 times, or over 3. Oh, then these could cancel. You could do it that way, I'm just saying. Just if you didn't have a calculator and you're trying to make it easier on yourself. But then at this point, then you still kind of need a calculator. Let's see what we get there. 7 times 13 times 3 times 11. So 3003. Okay, you could use the factorial buttons in your calculator and just do this here. But there is an actual command in your calculator for doing this. Yep. Let me show you guys. All right, so we could do it with just the factorials. I'm going to pull the 84 up. Okay, so we could go 15 and then math probability. All right, so 15 factorial divided by, now since there's 2 factorials in there, I'm going to need to put that in an exclamation point or a parentheses. So 10 factorial and then 5 factorial 3003. But if you guys notice in the math, right underneath or above it, you have NPR and NCR. Those are your permutation and combination formulas. So if I go to my home screen and I just write it in like this here, this 15C5, so 15, then math, probability, and CR, 5, it puts it in there. Nice, neat for me. So I don't have to do all that I just did. So math, probability, and CR. And then that PR, that's the next one, permutation. So in permutation, order will matter. Okay, so we have order does matter. It's going to be NPX. So N pick X. And then the formula for this, very similar, it's going to be N factorial over N minus X factorial, but that's it. It doesn't have that extra factorial. Okay, so for example, and this is when order does matter. So really if you guys can do this in your calculator, you really just have to read the question and determine if the order matters or it doesn't, and then know which calculation to use. Because you can do the rest in your calculator. Okay, so a club has 20 members. The members are to select 3 office holders for next year, president, secretary, and treasurer. They always select these holders by drawing 3 names randomly from the names of all members. The first person selected is president, the second is secretary, the third is treasurer. Determine the total number of officer arrangements for next year. So first person, so they're giving you an order, so now the order matters. So you just read through the context of the question. Okay, there's 8 people in the finals at the Olympics. In how many different ways can first, second, and third place occur? As opposed to there's 8 different people at the Olympics. How many different groups of 3 can podium? See the difference there? There's no order to just being on the podium, okay? But there is an order to first, second, and third place. All right, so then this would be 20 pick 3. So 20 P 3. So let's go to our calculator. We'll put the 20 in. And then math, probability, and PR, 3. 6,840. All right, so that brings us to our practice problems. So I'm going to give you guys 10-ish minutes. We'll see how many we can get done here. You got 5 problems here. And this is going to cover from the whole chapter, not just these 2 sections. Okay, random sample of 700 college students were asked if college athletes should be paid. The following table gives a 2-way classification of the responses. So you asked a student athlete and non-athletes. So if we add those together, we have 240 plus 10, so 250 student athletes, and 210 plus 240 is 450 non-athletes, and that would give us a total of 700. And in the survey, a total of 240 plus 210, 450 said they should be paid, and then 250 said they should not be paid. Okay, so let's look at our probabilities. So if one student is randomly selected from these 700 students, find the probability that this student is in favor of paying college athletes. So the total number that said they should be paid is right here, this 450 out of 700, which is going to give us 0.643. Second one, favors paying college athletes given that the student selected is a non-athlete. So our denominator is going to be restricted to non-athletes. Okay, so the non-athlete denominator is right here. That's 450. So our sample space is just restricted to the non-athletes. So they said, the non-athletes that said yes, right here, that 210. So 210 out of 450. And that is 0.467. Okay, is an athlete and favors paying college athletes. So, and this is out of 700. So the people that are athletes and also said yes. So we're just looking here, athlete should be paid. That's this 240 right here. So the athletes that said they should be paid. Here, here. And that is going to be 0.343. Okay, then is a non-athlete or is against paying student athletes. Okay, so this is going to be out of 700. And let's see here. Is a non-athlete or is against paying. So total number of non-athletes, 210, 240, so 450. Plus the people that are also athletes but say no. That's these guys right here. So 10. So 460 out of 700. Okay, so I pick one person, and it's just the possibility that they're either a non-athlete, doesn't matter what they said, so it's both of these, or they're an athlete that said no. So 460 out of 700 is 0.657. Any questions on that one? All right. I can show you at the end of class. We have only 8 minutes left. Okay, using the table below, showing the relative frequency of grades in a certain statistics class to determine the following probabilities. Okay, so what is the probability that a student chosen at random passed? A, B, or C? Yes, did you have a question? I'm sorry? What about B? Mm-hmm. Well, it would be A, B, or C, so we would want to add all of these probabilities here. So we would do 0.20 plus 0.31 plus 0.23. So we would add those probabilities, that would be 0.74. What is the probability that a student chosen at random did not pass? That's the other one. So that would be, what was it? 0.26. You could do 1 minus pass, so 1 minus 0.74, or you can add 0.14 plus 0.07 plus 0.05. Given that a student chosen at random passed, so now we're just looking at the people that passed, what is the probability that they got an A? So you had the probability of an A, or given that they passed, so 0.74 passed, and 0.20 out of the 0.74 got an A. So you would divide those, which would be 0.27. Yes. Okay, number 3, the probability that any given person is allergic to a certain drug is 0.03. What is the probability that none of these randomly selected persons is allergic to a drug? Assume all 3 are independent. Okay, so we're doing it 3 times. So what we want to do here is we want to find the probability that someone is not allergic. So that would be 1 minus the probability that someone is allergic. because that's what we're given. So the probability that someone is allergic is 0.03. So that would be 0.97. So the probability that someone is not allergic is 0.97. So then what we need to do is the probability that we're doing 3 people, it would be the probability that someone is allergic, or sorry, not allergic, times the probability that someone is not allergic, times the probability that someone is not allergic. So you're multiplying the probability 3 times. So 0.97 times 0.97 times 0.97. Okay, because these are independent. So the independent probability, we are multiplying. We don't need to subtract anything out. So 0.913. Okay. So the following table depicts the Nobel Prize winners in some categories from 1901 to 1998. And we're going to answer questions. All right, so if we want to add all of these, this is going to be 43, 107, 8, 18, 71, 198. So this is going to add to a total of 445. And then for chemistry, this adds to 110. Medicine, 144. And then physics adds to 191. So if a winner is chosen at random, what is the probability that he or she won the award in physics? So you would do the total physics, 191, out of the total, 445. And that would give us 0.429. Part B, if we choose at random, what is the probability he or she is from France? So we'll go to the France column, go all the way across. There's 43 total from France. We're still just choosing at random, so out of the total of 445. And that gives us 0.097. Okay, if a winner is chosen at random, what is the probability that he or she is from the United States, given that the award was won in the field of medicine? So, given medicine, so our denominator will change to just medicine. So I'm just looking at this sample space right here, 144. So out of 144, how many are from the United States? 82, which is going to give us 0.569. Yes. I know. I'm going to do this last 2 parts here. If a winner is chosen at random, what is the probability that he or she won in the field of medicine, given that he or she was from the United States? So then that would be, for the denominator, the total in the US, which was 198. Then in that sample space of a total of 198 from the United States, we would want the number of people in the US that won an award in medicine, which is 82. So that's going to be a 0.414. And then part E, if a winner is chosen at random, what is the probability that he or she won the award in physics or chemistry, given that he or she is from the Soviet Union? So for the Soviet Union, looking back at the table, there's a total of 18 in the Soviet Union. Okay, so total Soviet Union is 18. So then you have, for the first one, physics is in the Soviet Union, 10 plus, because it's or, chemistry from the Soviet Union is 7. And then 10 plus 7 is 17 out of 18. They only had 1 in medicine, so there was just 1 left. 0.944. Okay, so for this last problem, we have a simple random sample of adults living in a suburb in a large city was selected. The age and annual income of each adult in the sample were recorded. The resulting data are summarized below. All right, so is it added all up? The totals are on here, but on yours, but for some reason mine is not. So it's a total of 207, and then this is 50, 89, 53, and 15. Okay. All right, so part A, what is the probability that a person chosen at random from the sample will be in the 31 to 45 age category? Okay, well that's total. So there's a total of 207. And then 31 to 45 is right here. So we had a total of 89 there. So 89 over 207 is going to give us a 0.429. Part B, what is the probability that a person chosen at random from those in the sample whose incomes are over 50,000 will be in the 31 to 45 age category? So this is probability that it's over 31 to 45 given over 50K. Because we're only choosing what is the probability that person chosen at random from the sample whose incomes are over 50,000. So now choosing that their income is over 50,000 is the given part. So that's going to be out of, let's see, 96 total, over 50,000. And then in this sample space of 96, there's 35 out of the 96 who were in the 31 to 45 age category. So that's a 0.365. Okay, so whose income are over 50,000 will be in that category, so it's restricting that sample space. And then based on your examples, or your answers to parts A and B, is annual income independent of age category for those in the sample? Okay, well, do these equal to each other? No. Okay, since the incomes of those in the 31 to 45 age category are not equal to those whose income is not 50,000, over 50,000 in the 31 to 45 age group category, these are no, they are not independent. And that is it for chapter 3.